quality factor in terms of energy decay. Okay, quality factors in terms of energy decay quality factor in terms of energy decay. Okay, the quality factor of a forced oscillator, the quality factor of a forced oscillator Q equal to 2 pi multiply average energy stored upon energy dissipated per cycle. Equal to 2 pi E average upon T multiply P average. Okay, the instantaneous value of energy, the instantaneous value of energy equal to kinetic energy plus potential energy at any time. Okay, then the instantaneous value of energy, kinetic energy plus potential energy at any time. The kinetic energy equal to 1 by 2 m dy by dt square, and potential energy equal to 0 to y sy dy equal to 1 by 2 sy square, and total energy equal to 1 by 2 m dy by dt square plus 1 by 2 sy square. If the applied driving force is represented by F, F equal to F naught cos omega t. Okay, that is applied driving force. Then y equal to F naught upon omega Zm sin omega t minus phi, and dy upon dt equal to F naught upon Zm cos omega t minus phi, and that is equal to 1 by 2 m F naught upon Zm whole square cos square omega t minus phi plus 1 by 2 s by omega square F naught upon Zm whole square sin square omega t minus phi. Okay, then for a complete cycle, the average value of cos square omega t minus phi equal to, for average cycle, the average for a complete cycle, the average value of cos square omega t minus phi equal to 1 by t 0 to t cos square omega t minus phi into dt equal to 1 by 2. Okay, and the average value of sin square and the average value and the average value of sin square omega t minus phi equal to 1 by t 0 to t sin square omega t minus phi into dt equal to 1 by 2. Okay, then E average. Okay, then E average equal to 1 by 4 m f naught upon Zm square plus 1 by 4 s by omega square f naught by Zm whole square. Okay, that is 1 by 4 m f naught upon Zm square and 1 plus s by m omega square. Okay, omega square, that is 1 by 4 m f naught upon Zm square and 1 plus omega naught square by omega square. Okay, and P average and average power equal to f naught square upon 2 Zm cos phi equal to f naught square upon 2 Zm into r by Zm equal to f naught square r by Zm square and by 2. Okay, then quality factor equal to 2 pi E average power upon T multiply average power equal to 2 pi by T into m by 2r into 1 plus omega naught square by omega square. At resonance omega naught equal to omega and 1 plus omega naught square by omega square equal to 2 and 2 pi by t equal to omega naught and q equal to m omega naught by r. Okay, hence quality factor equal to 2 pi multiply average energy stored upon energy dissipated per cycle. Energy dissipated per cycle gives the definition of Q in terms of energy decay. Gives the definition in terms of energy decay. Okay, energy decay. Next, figure of merit. Okay, figure of merit. Okay, figure of merit. Okay, figure of merit. It is defined as the ratio of the frequency the ratio of the frequency. The ratio of the frequency at velocity resonance at velocity resonance the ratio of the frequency at velocity resonance maximum velocity response. Okay, maximum velocity response to the full bandwidth at half maximum power, at half maximum power. Okay, it is the ratio of the frequency at velocity resonance maximum velocity to the full bandwidth at half maximum power. Then figure of merit equal to frequency at velocity resonance upon full bandwidth at half maximum power. Full bandwidth at half maximum power. That is omega naught upon omega 2 minus omega 1. That is omega naught m by r. That is q, where omega 2 minus omega 1 equal to r by m. Okay, equal to r by m, where q is the quality factor. Quality factor or measure of sharpness of resonance. Okay, quality factor or measure of sharpness of resonance. Okay, the figure of merit or quality factor measures the sharpness of tuning. Higher the figure of merit for a given resonance frequency, smaller is the bandwidth, sharper is the tuning. This fact is used to increase the selectivity of radio and TV sets. The sharpness of response of a circuit allows radio signal RF and VHF video signal, okay, to reproduce without any interference from other signal of frequencies close to it. Okay, the figure of merit or quality factor measures the sharpness of turning. Okay, measures the sharpness of tuning. Okay, higher the figure of merit, higher the figure of merit for a given resonance frequency, for a given resonance frequency, for a given resonance frequency, smaller is the bandwidth, smaller is the bandwidth, smaller is the bandwidth, sharper is the tuning, sharper is the tuning, okay? This fact is used to increase the selectivity. This fact is used to increase the selectivity, of radio and TV sets, okay? The sharpness of response of a cycle, the sharpness of response of a circuit allows radio signal RF or VHF, okay, to be reproduced without any interference from other signals of frequencies close to it, okay? Next, physical significance of quality factor. Physical significance of quality factor, okay? Physical significance of quality factor. Physical significance of a quality factor. Physical significance of quality factors, okay? Quality value represents the sharpness of absorption curve. Larger the value of quality factor, sharper is the peak value of absorption curve. Okay? If larger the value of a quality factor, larger the value of quality factor, larger the value of quality factor, sharper quality factor, sharper is the peak, peak value of absorption curve. Second point. Quality value also measures the amplification factor. Thus, at displacement resonance, the displacement at low frequency if simplified by Q times. Q value Q value also measures Q value also measures the amplification factor. The amplification factor thus at displacement resonance, the displacement at low frequency at low frequency is amplified by Q times. Okay. Next point. Q value of amplification factor. Q value of amplification factors. Q value as amplification. Q value as amplification factor. Okay. Maximum amplitude equal to F naught upon omega dash R, where omega dash equal to under root of S by M minus R square by 4M square. The amplitude A equal to F naught upon under root of 4B square omega square plus omega square minus omega naught square whole square, where F naught equal to capital F naught upon M. Okay. When omega tends to 0, the amplitude A naught equal to F naught upon omega naught square, that is F naught upon S by M, that is capital F naught by S. Okay. The ratio of the maximum displacement of the maximum displacement of the maximum at resonance to the maximum displacement at resonance to the maximum displacement when the frequency of the applied force approaches zero is known as amplification factor. Okay. The ratio of the maximum displacement at resonance to the maximum displacement when the frequency of the applied force approaches zero is known as amplification factor. Okay. Let us study resonance in LCR circuit in detail along with the quality factor for that we will first write an expression of current in the circuit in the steady state both when the applied EMF is equal to current in the electric circuit RLC LCR circuit. Okay. Series LCR circuit, series LCR circuit, series LCR circuit, series LCR circuit. Okay. Consider an electric oscillator consisting of an electric circuit containing a resistance R, inductance L, and capacitance C in series as shown this figure, connected to an AC source, for which the EMF is represented by E equal to E naught e to the power I omega t, omega being the angular frequency of the applied alternating EMF. Such a circuit behaves as a drive-in oscillator. The loss of energy in the resistance is compensated by the supply of energy from the AC source, just as the loss of energy due to friction in a mechanical drive-in oscillator is compensated by the driving force. If I is the current at any instant, then fall of potential across the resistance. Fall of potential across fall of potential across the resistance resistance R equal to Ri. Okay. If the current varies at rate di by dt, then the voltage required to overcome the back EMF E in the inductance L di by dt. Okay. If the current varies at the rate di by dt, then the voltage required to overcome the back EMF in the inductance L di by dt. Okay. Then if Q is a charge accumulated on the capacitor at that instant, then fall of potential across the capacitor, and fall of potential then fall of potential across the capacitor, capacitor equal to Q by C. Okay. Hence the voltage equation at any instant is given by voltage equation equal to Ri plus L di by dt plus Q by C equal to E naught e to the power I omega t. Okay. Now I equal to dq by dt and di by dt equal to d square q by dt square. Hence r dq by dt plus l d square q by dt square plus q by c equal to e naught e to the power I omega t. Okay, I omega t. Then r l d square q by dt square plus r dq by dt plus q by c equal to e naught e to the power I omega t. E to the power I omega t. Okay. Then steady state. In the steady state, let one particular solution of the equation be q equal to q naught e to the power I omega t. Okay, where q is the complex quantity, where q naught is the complex quantity, q naught is the complex quantity. Then dq by dt equal to I omega q naught e to the power I omega t. Okay, and d square q upon dt square equal to minus omega square q naught e to the power I omega t. Okay, substituting in the equation number first, you can let this is the equation number first. This is the equation number first. Okay, you can let this is the equation number first. Okay, then substituting in equation number first, we have substituting in equation number first, we have minus omega square L plus I omega R plus 1 by C Q naught e to the power I omega t equal to e naught e to the power I omega t. Okay, then this relation is true for value of I. This relation is true for value of I, value of t. This relation is true. This relation is true for all values, r values of t. Then q naught equal to e naught upon I omega R plus 1 by C minus omega square L. Omega square L equal to minus E naught whole upon omega R minus I 1 by C minus omega square L. Okay, omega square L. Okay, equal to minus I E naught whole upon omega R plus I L omega minus 1 upon C omega. Then this is converted in or equal to minus I E naught upon omega ZE, omega ZE, omega ZE. This is the equation number second. This is the equation number second. Okay? Where this is equation number second, where this is equation number second, where ZR, where ZE vector is complex quantity called the electric impedance, electric impedance or effective resistance and ZE vector equal to R plus I L omega minus 1 by C omega. Okay? R is the ohmic resistance and circuit is X. R is the ohmic resistance. R is the ohmic resistance and L omega minus 1 by C omega equal to X is called the total reactance. It's called total reactance. Okay? And L omega equal to XL, M omega equal to XL, and represents the reactance due to inductance. Reactance due to inductance, and XC represents the reactance due to capacitance. Okay? Due to capacitance, and then put R equal to ZI cos phi. Now put R equal to ZE cos phi and L omega minus 1 upon C omega equal to ZI sin phi, so that ZE equal to under root of R square plus L omega minus 1 upon C omega का whole square and tan phi equal to L omega minus 1 upon C omega upon R, and ZE equal to ZE cos phi plus I ZE sin phi equal to ZE common cos phi plus I sin phi equal to ZE e to the power I phi. Okay? Substituting in equation number 2 we get substituting in equation number second we get Q naught equal to I E naught upon omega ZE to the power I phi. Okay? Then Q equal to Q naught e to the power I omega t, and Q equal to minus I E naught psi E naught minus I E naught e to the power I omega t upon omega z e to the power I phi equal to minus I E naught upon omega z e to the power I omega t minus phi. Okay, the current I in the electric circuit similar to the velocity v in a mechanical oscillator is given by I equal to dq by dt. I equal to dq by dt. I equal to dq by dt. I equal to dq by dt equal to minus I and E naught and small e to the power I omega t minus phi upon omega z multiply I omega. That is I equal to E naught upon z e to the power I omega t minus phi. Okay, I omega t minus phi. Okay, then I equal to I naught e to the power I omega t minus phi. Okay, where I naught equal to E naught upon Z. The current I and the applied EMF E are not in phase. This is the equation number 4. And this is the equation number 3. Okay, then the current I and the applied EMF are not in phase. Okay, the current I and applied EMF not in phase. There is a phase difference of phi between applied EMF and current, and the phase difference is phi. The phase difference is phi. Okay, first point, applied EMF equal to EMF E equal to E naught cos omega t. Okay, E naught cos omega t. Okay, then when the applied EMF equal to E naught sin omega t. It is a part of equation number 5. Applied EMF equal to E naught cos omega t. The applied EMF equal to E naught cos omega t equal to E naught e to the power I omega t can be put in the form. Okay, applied EMF equal to E naught cos omega t. Okay, the applied EMF equal to E naught I to the power I omega t can be put in the form E equal to E naught cos omega t plus I sin omega t. Okay? E equal to E naught cos omega t plus I E naught sin omega t. Okay, this is the equation number 5. This is the equation number 5. E equal to E naught cos omega t is the real part. This is the real part. Real part. This is the real part of the complex quantity E equal to real part of the complex quantity E equal to E naught I omega t. Okay, I omega t can be put in the form. Therefore, the steady state solution for the current I will be the real part of equation number 4, which may be put in the form, which may be put in the form, 1 minute, which may be put in the form, the form is, I equal to I naught. I equal to I naught e to the power I omega t minus phi equal to I naught cos omega t minus phi plus I sin omega t minus phi. This is equation number 6, and the real part is I equal to I naught cos omega t minus phi. Okay. Thus, when the applied EMF E equal to E naught cos omega t, the current is. Thus, when the applied EMF is equal to E naught cos omega t, the current is I equal to I naught cos omega t minus phi equal to E naught upon zeta cos omega t minus phi. This is equation number 7. This is equation number 7, where tan phi equal to L omega minus 1 upon C omega upon R, and ZE equal to under root of R square plus L omega minus 1 upon C omega whole square. Okay. Second point. Current in parallel to, second point. Applied EMF E equal to E naught sin omega t. When the applied EMF E equal to E naught sin omega t, it is dependent the part of equation number 5, which is present the vector operator I. There is the steady state term of the current I will also be that part of equation number 6, which is preceded by the vector operator I. Then I equal to I naught sin omega t minus phi equal to E naught upon ZI sin omega t minus phi. Sin omega t minus phi. Value of ZI and phi are given in part first above. Okay. And the second point. LC, current in a parallel LC circuit. Current in parallel parallel LC circuit. LC circuit. LC circuit. Current in parallel LC circuit. Okay. Current in parallel LC circuit. LC circuit. What is LC circuit? We will be detailed study in electrical part of a parallel and series LC circuit, and this is AC current. This is AC source. This is AC source. E equal to E naught sine omega t, and this is inductance, and this is capacitance. This is capacitance. This is point current I, point A and B. This is U, C, and this is Q, charge, and current I2 on the through the capacitor, and current I1 through the inductance. Okay. Then in a parallel LC circuit, in an inductance L having a very low ohmic resistance, and a capacitor of capacitance C are connected in parallel, and AC source of voltage E equal to E naught sine omega t is connected at a point A. A and B. Suppose a current I flow through the circuit, and any instant let I1 be the current through the inductance L, and I2 through the capacitance C. Then I equal to I1 plus I2. Let the current through the inductance L vary at the rate di1 by dt. Then let the current through the inductor L vary at the rate di1 upon dt. Then E equal to minus L di1 by dt equal to 0, or L di1 upon dt equal to E naught sine omega t, and I1 equal to E naught by L integration of sine omega t into dt. Okay. Then that is minus E naught upon omega L cos omega t. Let the charge on the capacitor at any instant, let the charge on the capacitor at any instant be Q. Then Q equal to C E naught sine omega t. Current through the capacitor I2. Current through the capacitor. Current through the capacitor I2. Current through the capacitor I2 equal to dq by dt dq by dt equal to c omega e naught cos omega t, and substituting the value of I1 and I2 in equation number first we have, and this is the equation number first. Substituting the value of I1, substituting the value of I1 and I2 in equation number first. In equation number first we have I equal to I1 plus I2 equal to C omega E naught cos omega t minus E naught upon omega L cos omega t, okay, equal to C omega minus 1 upon omega L E naught cos omega t, okay, E naught cos omega t. Then that is C omega minus 1 upon omega L E naught cos omega t, okay, if cos omega t, okay. Then if C omega equal to 1 upon omega L, the current in the circuit will be 0. The current in the circuit will be 0. This will happen when C omega equal to 1 upon omega L or omega equal to 1 upon under root of LC or n equal to 1 upon 2 pi under root LC. The frequency of the applied AC voltage is equal to the natural frequency of LC circuit. Is that the frequency of the applied AC voltage is equal to the natural frequency of the LC circuit, okay. Thanks.